Wow, Mr. Leong, this red wine tastes really good, man.
Of course, it costs $300 eh. Of course it tastes good lah. But Mr. Tim, can you really tell me what is inside this wine that makes it taste so good?
Well, it's because of this molecule here,
Okay.
that makes wine taste so beautifully smooth and
Right?
nice. Yeah.
So if I take a look at the functional groups, it looks like there's going to be 5 OHs inside. So I think there's 5 alcohols inside the molecule.
Oh,
Is that
wait.
right? Oh.
Because to call it an alcohol, we say that the OH bonded to the carbon, it must be saturated, right?
Okay.
But out of the 5 of them, 4 of them are bonded to carbons that are unsaturated.
Right, and you notice that they are going to be in a ring with alternating double bonds. So I think that is going to be a benzene,
Exactly.
and a benzene attached to a OH is not called an alcohol.
It is called a phenol.
Oh, so that is probably
Yeah.
going to be the focus of today's lesson, right?
Yes. So cheers to phenol.
Cheers. Oh, hi, Mr. Tim. What are you up to today?
I'm trying to figure out which is more acidic. Is it going to be my ethanol or is it going to be my red wine, which contains phenols?
Okay, so definitely you're not going to taste it like what you did just now.
Okay.
So what we can do over here is to use the indicator paper to see whether it's acidic or not.
Right. Okay.
Shall we try it?
Smart. Yeah, let's do it.
So I'll hold on to the red wine, which contains a phenol, and you'll be holding on to the alcohol, right? So ready when you are?
Yep, let's go.
Oh wow, that was fast.
Well, mine turned green.
Okay, so mine actually turned orange. Shall we take a look at the pH indicator chart to roughly know what is the pH of the solution? So for yours is green color.
Yeah.
So what pH would that be?
And green stays 7. Green means it's 7.
Okay.
pH 7. Yeah.
So that will be probably
Neutral.
Neutral,
Yeah.
right? But for mine is orange, so that will mean that it's going to be roughly around pH.
pH 3 acidic.
Right, it's acidic.
Yeah.
So in conclusion, we can say that phenol, which is present in red wine, is going to be acidic, but for alcohols, they are generally thought to be neutral. And today's lesson, we are going to pay attention to the chemistry that's behind them. Okay, so now let's go back to the encyclopedia and take a look at the chemistry that describes why your phenol is more acidic than your alcohol. Okay, now before we start, we have to think about acid-base equilibrium. We understood that all our organic molecules, if they're acidic, they're going to behave as weak acid. What does it mean to be a weak acid, Mr. Tim?
But weak acid means you dissociate reversibly.
Right.
You release H plus in water.
That's right. So you see a reversible arrow, and you are going to obtain this thing called the conjugate base.
Yep.
Remember again what Mr. Tim was a conjugate base?
Well, conjugate base means they differ from the weak acid by a H plus.
That's right.
So if the weak acid is ROH, conjugate base will be RO minus.
That's right.
Yeah.
So can I extend this question a bit further? Now, if let's say we have a stronger acid,
Okay.
do you think the position of equilibrium is going to lie towards the left or towards the right?
Well, if I'm a stronger acid, means I dissociate more fully, right? Which means my POA should be towards the right.
That's right.
Yeah.
So the stronger you are, the more your forward reaction will be favored, right? And in general, all kinds of chemical systems would like to favor something that is a little bit more stable. So therefore, in order to determine whether if someone is more acidic or not, we actually do not really focus on the acid. What we focus on is actually the conjugate base, okay? So our discussion from now on, right, when we talk about acidity, is always going to be focusing on the conjugate base, and more specifically, we're going to look at how stable the conjugate base is.
Wait, Mr. Leong, stable? What does it mean by stable conjugate?
Good question.
Yeah.
So more stable means that I'm going to pay attention to the charge, and I hope that this charge is going to get dispersed. Meaning that the negative charge is going to be spread across the entire molecule.
Right.
And we want to see what are the different methods to achieve that.
Okay.
Okay, now the first one is we're going to jump straight into the action. We're going to take a look at why phenols, they are actually more stable, or rather they are more acidic, and we shall take a look at the conjugate base.
Now, let's look at phenol. So what we have here is phenol dissociating in water to release H+. So this is your equation that you have here. Again, phenol, weak acid, reversible arrow. So remind yourself what Mr. Leong and I just mentioned. The more stable this conjugate base is, this phenoxide, right? Then the more the POE shifts to the right, and hence it's a stronger acid, okay? Now, to talk about stability of conjugate base, we must first talk about how to disperse this negative charge. But before that, I want us to focus on this benzene ring here. Now remember how we learned in arenes that in your benzene ring, you have this 6 pi electrons, yeah? Now, remind me again, Mr. Leong, notice that these p orbitals, right, they are parallel and they are adjacent. Now, what does that mean?
So this allows them to overlap extensively with each other, and the electrons inside there are going to delocalize across all these overlapping orbitals.
Right. So we say that the whole benzene here is actually resonance stabilized, like what Mr. Leong said. Now, here is something that is quite unique. You would realize that this lone pair on the oxygen is actually found in the p orbital. Now, look at what this means. If this lone pair, let me draw this in first. If this lone pair is found in the p orbital, again, this p orbital is parallel to the p orbital in the benzene pi system, okay? It's parallel, it is adjacent, which means what again, Mr. Leong?
So definitely they are going to overlap, and as a result, the lone pair that you say on the O is also going to delocalize inside.
Exactly. So do this here with me. So draw this lone pair here, inside this lobe here. Now, I drew the lone pair as a dot and a cross. The dot represents the oxygen's electron, and the cross represents the negative charge's electron, right? So like what Mr. Leong said, this lone pair, we're now delocalized into the benzene ring pi system. So I want you to draw this arrow with me. Tell yourself that there's lone pair that's housing the negative charge, has now been sucked into the benzene ring, and we have dispersed the negative charge. So we realize that this conjugate base is actually now stable, okay? And that's it. And because it's more stable, do this with me as well. Last thing, the POE for this equilibrium will now be shifted towards the right, and you will see that phenols are actually quite acidic.
That's a good one.
Yeah.
So shall we take a look at the alcohols now?
Let's go.
So we're going to take a look specifically at ethanol. So once again, we're going to start off with the dissociation equation.
Right.
We have gotten the conjugate base, which is known as the ethoxide ion. Now, when we look at any acidity, I just want to warn you again that you do not always focus on the acid. When we do the discussion, it must always revolve around the conjugate base. And we want to see whether if the conjugate base is stabilized through whether if the charge is being dispersed or not, right? Now, in this case, it's going to be a little bit special because when I zoom into the ethoxide ion, I do notice that there is going to be an alkyl group attached to the O-. And what kind of effect are alkyl groups going to exert, Mr. Tim?
Alkyls are always electron donating.
That's right. So it's electron donating, which means that the alkyl group is going to push electron density towards the O-. And can you tell me what's going to happen to the charge on the O-?
This is horrible. Instead of dispersing it, we're actually giving electrons to it. We are intensifying this negative charge.
Right. And as a consequence, is it going to stabilize or destabilize it?
Definitely destabilize this.
That's right. So if you manage to destabilize your ethoxide ion, it must mean that the position of equilibrium will shift towards the left. And that will cause the production of less H+, which essentially means that your ethanol is going to be not acidic at all. Now, in reality, your alcohol, we do not even call it acidic. We say that it is actually a neutral molecule. And in reality, we also understood that ethanol is even less acidic than water. I mean, come on, water is not even acidic in the first place, right?
Exactly.
So ethanol is even less acidic than that. So we never ever say that alcohols are acidic. We simply just say that alcohols are neutral. Okay, Mr. Tim, can you summarize this in the table for me?
Yeah, sure. So again, we know that phenols, they are stronger acids than alcohols. So what we have here is reaction with sodium. Now just remember, both of them have that hydroxyl functional group. So they would react with sodium for sure via an acid-metal reaction. Okay. Now, sodium hydroxide is a strong base. So because it's a strong base, it can only react with the strong acid phenol, but it can't react with the alcohol because it's a much weaker acid. Okay, so no reaction here. Now, last but not least, what we have here is sodium carbonate. Sodium carbonate is a very, very weak base, so we realize that it cannot react with alcohols, and neither can it react with phenols. Okay?
That's nice. So in general, these are how, in reality, that's what we see that describes the acidity. The more acidic it is, you're going to react with more different bases or reagents. Okay? Now, let's be a little bit more funky here. We are going to take a look at what happens if the phenol actually contains an additional side group. Now, this side group has a name. We call them a substituent. Now, it turns out this substituent, right, is going to have an impact on whether your phenol is acidic or not. Is it going to make it even more acidic or less acidic? Okay, so we always begin with the dissociation equation. We always focus on the
conjugate base.
That's right. So we always look at the conjugate base, and this is the conjugate base over here, the phenoxide and ion. Now let's take a look what happens if I decide to put an electron withdrawing group onto my benzene ring. Now, Mr. Tim, think about this. If I have an electron withdrawing group, can you tell me something, what's going to happen to the O- over here?
Well, if it's electron withdrawing, it's going to suck electrons from that ring, from the benzene ring even more. So it's going to disperse the negative charge even better.
That's right.
So therefore, this conjugate base is definitely going to be more stable compared to your boring phenoxide.
That's right. So at the end of the day, it means that you are going to make your new phenol, the one with the electron withdrawing group, more acidic than expected.
Exactly.
Okay. Mr. Tim, can you share with me what are some examples of electron withdrawing groups then?
You can actually just flip to your data booklet. It's right here.
So we are looking out for those functional groups that are deactivating. Sorry, they are deactivating, right?
Deactivating.
So some examples are over here actually. Okay, but you can actually find them. Like what Mr. Tim said, is going to be on your data booklet. Okay. Now, what's going to happen on the other hand is if I have a electron donating group. So you realize that everything is just the opposite. You're going to push electron density towards the O-, and what happens to the charge, Mr. Tim?
Again, it doesn't disperse anymore. It intensifies it, makes things worse. The conjugate base is now less stable, less acidic.
Yes, so therefore I can conclude for you. If you have an electron withdrawing group on the phenol, you are going to make the phenol more acidic than phenol. If you have an electron donating group, you are going to make that particular molecule less acidic than phenol. Oh my god, Mr. Tim, am I boring you?
Yeah, acidity is boring, man. I really want to talk about the chemical reactions of phenol.
Okay, sure. Go ahead then.
But as usual, again, we have to talk about whether phenols are nucleophilic or electrophilic. Okay, so let's go in. Now, phenols is a little bit tricky. You have two nucleophilic regions here. One on the left, the pi electron system on the benzene. We have seen that in arenes, electron rich. And again, the lone pair on the oxygen on the hydroxyl group on the right. Okay. Now, for just this first part, you'll be looking at the hydroxyl group of phenols and how that group is actually nucleophilic. Okay. Now let's compare with alcohol, same thing. Now, so if you guys notice the lone pair on the oxygen, again, it is next to a pi electron system. That lone pair in a p orbital, it is parallel and is adjacent to that pi electron system in the benzene ring. So once again, you will realize that those two p orbitals there, they will sideways overlap. Now, does that mean, do you think it's available, Mr. Long?
So once it delocalizes inside, your O has lower electron density, so I think it's going to be less available for donation to an electrophile. So I believe that's going to make it a less nucleophilic reagent.
Exactly, way less nucleophilic compared to your alcohol here on the right. Now again, alcohols, the R group, Mr. Long, donating or withdrawing?
So alcohols always exert the electron donating effect.
Okay, so because of that, it activates a lone pair. The lone pair now becomes more available and hence is more nucleophilic. Okay?
That's right.
Right.
So that's it. So we always look at the lone pair, the availability of a lone pair to determine its nucleophilicity.
Yes.
Right. So the second part of our discussion is going to be revolving around the benzene being a nucleophile. So we understood that benzenes, they are nucleophilic in nature because of the fact that they have delocalized pi electrons inside the benzene ring. So that's why they are going to be nucleophilic. Right. Now, if I take a look at the phenol over here, just like what Mr. Tim said, you see that the lone pair is going to delocalize into the benzene ring. Now, can you tell me what's going to happen to the electron density of the benzene ring, Mr. Tim?
Well, to the benzene ring, it receives these two electrons, so now the electron density has went up.
Yes, that's right. So you're going to increase electron density in the benzene, and that's going to cause my benzene to be more nucleophilic. That's right. So in the context of a typical benzene ring, you do not see such a delocalization happening from the O, so therefore it is going to be less nucleophilic. Right? Now, just to conclude for you, acidity and nucleophilicity, they are really different ideas. What does acidity depend on, Mr. Tim?
Well, again, acidity depends on the stability of the conjugate base.
That's right.
Right.
So that is the thing that you must focus on, always on the conjugate base, right? Stability of the conjugate base. How about nucleophilicity?
How available that lone pair is.
That's right. So it's about the availability of the lone pair to be donated into a electrophile.
Correct.
So Mr. Tim, can you help me to summarize the last part for me?
Yes, of course. So again, so in alcohol here is your ROH and your phenol here is the benzene ring with the OH, right? So once again, remind yourself, your phenoxide ion this conjugate base was more stable and therefore phenols were more acidic, right? We have that there. But again, if you focus on the hydroxyl functional groups of phenols and alcohols, right, you will realize again, because the lone pair on the oxygen delocalizes into the benzene ring, the lone pair is not available, and hence less nucleophilic.
That's right.
Okay. Okay. Now, finally, we just spoke about the nucleophilicity of phenols. Now we can finally talk about the reactions of phenols. But just before that, I want you guys to remember again, alcohols, right, can behave as nucleophiles and electrophiles. So you can see this here. If you put a nucleophile and you push it to an alcohol, a normal alcohol, the nucleophile can attack the R group there, or the carbon, because the carbon is electrophilic, and it breaks that OH, the CO bond, and releases the OH minus, right?
Yep.
Now, if I try to do this with a phenol, you will realize that this does not work. Because Mr. Leong, that carbon there, right, in the phenol ring, that's holding on to the oxygen, is that carbon electrophilic?
Now, this carbon is part of a benzene, and we all understood that benzenes, they are having high electron density, so I highly doubt that that carbon is going to be electron deficient.
Exactly. So when a nucleophile tries to approach that carbon, it repels. Phenols do not behave as electrophiles, okay? So do notice the difference. Now, however, like we mentioned just now, both alcohols and phenols, they both can behave as nucleophiles. So again, the focus here is on a hydroxyl functional group. Expose that lone pair for me on the oxygen and draw it, attack the electrophile. That's for an alcohol, okay? And for phenols, we can do the exact same thing.
All right.
Okay? Now, just before we go into the first few reactions that we're going to see, let me just remind you again, okay? Now, phenols are weaker nucleophiles than alcohol because again, the lone pair on the oxygen in the phenol has been delocalized into the benzene ring, okay? So to make phenol a stronger nucleophile, the first thing we have to do, which is 8.1 and 8.2, we have to take the garbage nucleophile phenol and make it into a stronger nucleophile, right? By granting it that negative charge. So we either use sodium solid, right, the acid-metal reaction that we did see in alcohols, or we can use a strong base, sodium hydroxide, right?
So yes, that's right. So in general, 8.1 and 8.2 is illustrating the fact that my phenol is usually acting as a nucleophile. This works the same as 8.7 as well.
Yep.
So these reactions will be gone through in class. So these three are where your phenol acts as a nucleophile. Now, we also understood that for any kinds of reactions, right? I mean, the OH is going to participate in its own reaction. Now, it turns out your benzene ring is going to participate in another set of reactions as well. So we saw this under arenes, right, Mr. Tim? What kind of reactions do they usually undergo?
Electrophilic sub.
Yes, that's right. Now, the reason why is because, once again, your benzene is going to be nucleophilic. It has high electron density. It acts as a nucleophile. It is going to undergo electrophilic reactions, right? It's going to undergo substitution because it wants to prevent any destruction of the resonance stabilized ring.
Yes.
So, reactions 8.3 to 8.6, right, are all electrophilic sub-reactions. So, please help me to label them together with me. They are reactions on the benzene, when the benzylic hydrogen, the hydrogen attached to the benzene, is going to get replaced with other atoms. Okay. Now, I do want to talk a little bit more about the reagents and conditions over here. The reason is because you notice that your OH over here, your phenol, your lone pair is going to delocalize into the ring. Now, can you tell me what's the consequence of that, Mr. Tim?
Then, therefore, if it delocalizes into the ring, it makes the benzene now a stronger nucleophile. Okay?
And that's going to make the benzene ring more susceptible to electrophilic attacks.
Electrophilic attack.
That's right. So what's the consequence in terms of the reagents and conditions then?
So again, it's going to be milder, right? Because now the benzene is a stronger nucleophile, it's going to be milder. Now, but not only that, I want you to also realize, if you guys can remember from the chapter in arenes, your OH functional group, right, when it's attached to a benzene, it is not 3-directing, it is 2,4-directing. Okay?
Yep. So these are the two major things about electrophilic substitution.
Yes. Okay, the last thing that we have here is also characteristic tests and distinguishing tests for phenols. Okay? Now, the first one that we have is adding neutral FeCl3, and I'm so sorry, this one you have to accept it. When you add in neutral FeCl3, it will form this gigantic, monstrous complex here. You don't have to know this for now, you just need to know that when you add in FeCl3, you see this purple coloration, this violet coloration of this monster molecule here. Okay?
Now, the second test is going to be something that you have seen before. This was a reaction that was covered in class. We're going to add bromine water into the phenol. So there's going to be a series of observations you can make. First of which, being the most important, is when you undergo reaction electrophilic sub for phenol, you're straight away going to achieve tri-substitution, right? And this particular structure is going to give you a white precipitate. So that's observation number one. You start to see a white precipitate. All right. Now the second one is quite obvious because you're using bromine, right? What color is bromine water?
Dark brown.
Dark brown or orange color.
Yep.
And the moment you react away, the color is going to
turn colorless.
Yes, it's going to decolorize, right? So that's observation number 2, right? So this number 1, this number 2. And finally, the last one may not be entirely obvious, is the fact that you're going to give off my HBr, right? Now this HBr is usually going to be seen as steamy white fumes, but this may not happen very often or very obviously. The reason is because we are doing this under aqueous environments. HBr is soluble in water, so chances are you don't really see a lot of these steamy white fumes coming out. Okay, so I'm going to just put this as number 3 over here, but if I were to ask you to rank them, this one should be the last one. Okay, so that's it. These are the 2 different tests, chemical tests for phenols. That's all the content that we have for today. We'll see you in class soon. Bye-bye.